All right, let's get right into it. For basically all of human history, we've had this constant, deadly companion, Mycobacterium tuberculosis. You see, this thing is an absolute master of survival. It's this ancient, microscopic enemy that has perfected the art of hiding out inside our own bodies. So today, we're going to unpack its survival playbook, and we're going to look at the secrets that make it one of the planet's most successful and most dangerous pathogens. And no, this is not some problem from the history books. Even with all of our incredible medical advances, tuberculosis is still responsible for over 1.13 million deaths every single year. That number is just, wow. It really tells you what a formidable adversary this is, and exactly why figuring out its survival tactics is quite literally a matter of life and death. So this brings us to the central mystery, right? The TB bacterium can infect you and then just go completely quiet. We're talking for decades, hiding from our super powerful immune systems and even our best antibiotics. It goes into what's called a dormant state, kind of like suspended animation. The big question is, how? How on earth does it manage to survive when it's basically switched itself off? To really get its strategy, you first have to appreciate its history. This isn't just some random germ. Oh no. This is a cunning survivor that's been locked in an evolutionary arms race with us for thousands and thousands of years. Just look at this timeline. We've been throwing everything we've got at this thing for over a century. The first vaccine came out way back in 1921. Then we discovered these powerhouse drugs, right? Streptomycin in 44, rifampicin in 63, and more recently, the real game changer, bedaquiline in 2012. For more than 100 years, our best science, our best medicines, and yet it's still here. That incredible resilience is what we're going to unpack. Okay, so the key to its whole strategy is this idea of dormancy. You can think of it as the bacterium's ultimate superpower. It basically puts itself into a deep, deep sleep. It stops making copies of itself, and this is the crucial part, it powers down its metabolism to the absolute bare minimum needed to just stay alive. This makes it practically invisible to our immune system and, really importantly, resistant to drugs that are designed to kill active, growing cells. So how does it actually pull this off? Let's break down its secrets, one by one. And we'll start with the very first thing it does when the going gets tough. You know, the first rule of survival is pretty simple. Don't waste energy. So when MTB finds itself in a hostile spot inside our bodies, like, say, deep inside a lung lesion where there's almost no oxygen, its first move is to slam on the metabolic brakes. It goes into this basal state, hoarding its energy currency, a molecule you might have heard of called ATP, getting ready for the long haul. But what happens when its main highway for producing energy gets blocked? Well, this is where MTB gets really clever. It's got a backup plan. It's like it has a built-in GPS that knows all the metabolic backroads. Now, I know this slide looks a bit like a complicated circuit board, but just think of it as the bacterium's energy factory. The main pathway, that's the one in green, is like a superhighway. It's incredibly efficient, but it needs a ton of oxygen to work. When the oxygen starts to run out, MTB does something brilliant. It reroutes everything. It jumps onto an alternative path, the one you see here in red, and it uses a different set of tools, like this enzyme called SIDAB, to keep the lights on. And this slide really lays it out perfectly. The standard path is that superhighway, fast, powerful, great for when there's plenty of oxygen. But the alternative path? That's more like a rugged off-road trail. Sure, it's less efficient, but it gets the job done when the highway is closed. And that allows MTB to keep chugging along, making just enough energy to survive in that suffocating, low-oxygen environment inside our lungs. And this insane adaptability goes right down to the nuts and bolts of its machinery. Its third secret is hidden in the unique design of the molecular engine that actually builds its energy. Okay. Check out this incredible piece of molecular machinery. This is the F-ATP synthase. It's literally a tiny rotary motor, a biological turbine that spins to generate ATP. But the MTB version has some special custom parts, especially in what's called the alpha subunit. And that custom part gives it a very special ability that is absolutely critical for its survival. And here it is, secret number 3. You see, any motor can accidentally run in reverse. But when this motor runs backward, it doesn't make energy, it burns through it. So MTB has evolved this unique built-in safety brake in that alpha subunit that stops this from happening. When it's in that dormant state where every single molecule of ATP is precious, this brake prevents the engine from wastefully spinning backward. It's all about conserving every last drop of fuel. So the bacterium can slow way down, it can take detours, and it can prevent waste. But what happens when we hit it directly with a powerful drug? Well, this reveals its fourth and maybe its most sophisticated secret. It can rewrite its own operating system on the fly. The moment a drug like bedaquiline starts attacking its energy engine, it's like a fire alarm goes off inside the cell. On the left, you can see this threat activates these master regulators. Think of them like cellular bosses named RV0324 and RV0880. Now look to the right. These bosses immediately order a complete metabolic rewiring. The bacterium reroutes all its internal chemistry, fires up backup systems, and even turns on these tiny pumps to literally spit the drug back out. It is an all-out coordinated defense to survive a chemical attack. For a long time, these secrets made MTB seem almost invincible. But here's the twist. Scientists are now taking the bacterium's greatest strengths and turning them into its biggest weaknesses. This quote really says it all. The drug bedaquiline, which directly gums up the works of that unique ATP synthase engine, was a massive breakthrough. It proved that if we can understand MTB's unique survival kit, we can design drugs to specifically break it. Its own specialization has become its Achilles heel. So how does this all fit together? Well, now that we've decoded the bacterium's playbook, it's become our battle plan. We know it slows its metabolism down, so we hit it with drugs that mess with its energy balance. We know it uses those metabolic backroads, so now we're designing inhibitors for those alternative enzymes, like CyDAB. We know it has that unique engine, so we jam it with drugs like bedaquiline. And we know it tries to rewire itself, so we fight back with combination therapies that block all its escape routes at once. By understanding how Mycobacterium tuberculosis survives, we've basically created a whole new generation of weapons to fight it. But you have to remember, this is an evolutionary arms race that's been raging for millennia. The bacterium has a survival plan, and now, finally, so do we. The critical question that's going to determine the future of this disease is simple. Who's going to adapt faster?